The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseWare continue to offer high-quality educational resources for free. To make a donation or view additional materials from hundreds of MIT courses, visit MIT OpenCourseWare at ocw.mit.edu.
Okay, welcome. This is great. It almost looks like beginning of the fall, at least outside. So, but it's IAP. So, what we are going to do is, I think it's going to be a very exciting month. And mainly the reason for doing this course is, I think we are about a software crisis. So there's an interesting quote I want to start with. This is somebody very famous in computer science who spoke during his Turing award lecture. I mean, his point was, when the computers were small, there was no problem. When computers got bigger, this pesky software started having problems. So the first software crisis, in fact, happened around in 60s and 70s. The problem for the first software crisis was people were writing assembly language programs. When the computers were small and memory was small, it was completely doable, no problem. But as computers became larger and larger, it became very hard to write assembly language programs. And what you needed is some kind of abstraction and portability. So you should be able to go every 2 years, do not have to rewrite the programs in there. So you need portability and you need some level of abstraction. So what that means is instead of writing all assembly hacking and dealing with every hardware feature, you can race about that. And the way we solved it, and that generation, is we came up with these high-level languages like Fortran and C. And what those did was they kind of provided a common machine language across these machines. And so what this did was they looked at all these machines those days, the uniprocessors, and kind of abstracted out. First of all, all the common properties is made it available for the programmer. So it didn't really let the program go too far away from the machine. But it abstracted out all the differences. So by doing that, we managed to get these languages like C and Fortran, work very fast, pretty efficient, and working through this thing. So that's how we avoided the first software crisis. And I think there's a lot of really good work happened, and then few people got Turing awards for doing these kind of things. And then we faced the second software crisis in 80s and 90s. The problem there was, C was great if two guys sit in a corner and write a program. When Microsoft started programming Word 3, with about a few hundred programmers, the problem was the bugs never went away. The project was supposed to finish in a year. It lasted 3 years, and bugs keep coming and coming, and they had no idea when the project was going to finish. Because the way you write in a small piece of code really didn't scale. And this was a huge crisis for people. Said we will never be able to write large programs because these programs will never work. They're going to be brittle. And the problem there is we want to be able to build software that's composable, malleable, and maintainable. So software multiple people should be able to do it, compose it, and when requirements change, it should be easy to change and easy to maintain. Interesting thing is we never cared about high performance at that time. Moore's law. This nice laws there out there is trying to take care of that. The way we solved that crisis, again, a lot of people got very famous for doing that, is came up with things like object-oriented programming languages. C#, C++, and now C# and Java basically made it possible for now hundreds, if not thousands of people to develop software. If you look at something like new Microsoft products coming out, thousands of people are involved in it. And still they managed to get it out on time. And also we did a bunch of better tools, things like component libraries and tools like Purify. And we developed a lot of software engineering methodology to develop software. We made it more of a process than kind of ad hoc art form. This is great. So here we are today. We are very happy, a lot of programmers here. Unfortunately, programmers are pretty oblivious to what's happening in hardware. We don't care. Programmers don't have to know about what things are running. We have these nice virtual machines. And of course, Moore's law, this great new thing, is going to come and take care of all of us. And if you want speed, just wait for 6 months. The machines will be faster. And that's the thing we have been going on. And nice thing is these programs written even in 70s, still run probably 2-3 orders of magnitude fast, because processors today are literally fast. And this abstraction gave us huge amount of power. Just say, don't care what's underneath. We are going to sit up there and just basically program. We were very happy with that. The problem is we are running into an issue in here. So we are at the beginning of this third software crisis, what I call the software crisis due to the multi-core menace. So multi-core for hardware people is a good opportunity, but software people is kind of a menace in there. Problem is sequential programs are left behind by Moore's law. And as you see, probably a lot of you know that you are not going to get performance on sequential programs, increased performance in there. We have to deal with this. And we need to support, the key thing here is, so why don't we just stop? Say, okay, good. We have the programs, machines run today very fast, is that good enough? The problem is we won't evolve. We need to support new features, we need to support things like large data sets in the same programs, and we kind of keep expecting a certain performance gain every year. To sustain portability and malleability, we assume that every few years the machine's performance will double, because we believe in that. Like, for example, Microsoft Word at the beginning, 10 years ago, it still worked. But it didn't have spell check running back in the background. We didn't deal with very large images. We didn't deal with XML kind of formats in there. And then, of course, next generation, we probably won't have integrated video, audio, voice recognition, all those things in there. And we need that power. We rely on that power. And this is going to be a big problem because sequential programs are stuck. It's not going to provide that power anymore. And it's critical. This kind of power is critical to keep up the current rate of evolution. And if we get stuck there, we are going to have a big crisis happening. So how is this happening? So I talked about Moore's law. So this is the obligatory side of Moore's law. So if you look at it, going from even before 1970s, we had this amazing growth in number of transistors available. So Moore's law doesn't say anything about performance. It says about number of transistors available on a die. Every 18 months it doubled. So this basically, some people even say, this is the basis of this last 2 decades of economic expansion, because we got all this amazing power because of this kind of growth in here. The problem is, if you look at performance, it's flattening out. So this is spec numbers. That's kind of the way you measure performance, is have this set of programs that we can keep running on these machines. And we keep running on these same machines, even though we are getting twice the amount of transistors. This is kind of flattening out. And then for last few years, it's kind of almost constant. We are not getting anything in there. And so we are still running from the fumes of that amazing growth rates we had in this time. And now we are kind of flattened out in here. And why is this? And the main reason for this is, I will talk about 4 things. One is power consumption, wire delay, and DRAM access time, and diminishing returns. So I will go a little bit into these details to kind of give you an overview why this is happening. The first thing is power. So as we go about, we keep taking more and more power. And right now, if you look at the 1 volt rate, that normally this 1 point some volt that this processor run, this draws more current than any of your houses back home. Okay, I mean that's amazing. I mean the houses probably draw like 150 watts, 150 amps, and in 1 volt it's 150. We are drawing about 150 watts. So this is like that much current going to these things, and heat, and it's a big issue. So this still shows, okay, we are flattening out. But another interesting thing is power efficiency. So we are trying to use these transistors. We are trying to do more and more out of these transistors. And if you look at how much watts you are spending on to get one of those spec rates, that's based how much to do the same amount of work, we are spending a lot more power, because we are building these things that have very marginal return today. Okay, that is the problem in building the current superscalar type things, because it doesn't go, this power efficiency. This is why Google is building their shops next to the Grand Coulee Dam, because they are sucking in so much power, because the power efficiency is a big issue for them. And today, microprocessor, the cost of it is more than purchasing. It's basically feeding it with power and cooling it. So another problem is wire delay. So we want to, if you try to build this monolithic large processors. So what happened is, in the good old days, within a clock cycle, in a processor dies this side, you can basically send a wire from one end to another processor still within 1 clock cycle. So if you are building this monolithic thing, it's almost like sitting in a room. When I talk, the other end of the room, they will hear about it in instantaneously because you are talking slowly, or the thing is you're clocking slowly in here. And today, we are around this area. So what that means is in a clock cycle, you can't get a wire for more than small part of the chip. So it's almost like trying to communicate in this building. So if I want to tell something to everybody, I can't broadcast. I have to tell somebody, has to go to the next door, tell somebody. To get the information through the entire thing takes time. And as we go more and more, this is going to be harder and harder and harder. And what that means is trying to build large monolithic processors like we did to keep the Moore's law kind of performance going is not working. And we are having this problem. Interesting third issue is DRAM access time. So what's happening is microprocessors are going like this. Access time, it's getting performance getting faster and faster. DRAM gets doubled only about every 10 years. And because of that, there's this interesting mismatch. If you are trying to get to DRAM, if you put things in DRAM, it's almost about probably 10 years ago, that kind of like latency we had to the disk is now we are having to DRAM. So the way we look at this, actually, the cost of it is going to get big, and it's also a power issue because if you're on chip, it's hundreds of probably 2 orders of magnitude cheaper to get to a word on chip than go all the way outside, get to the DRAM, and get things out. And so between power and this is also creating a huge amount of issue, that impossibility for us to keep this kind of Moore's law type performance keep going. The final thing is diminishing returns. So if you look at 80s, that is the year of superscalers. We had amazing performance improvements. So for example, when you started the decade, every CPI means clocks per instruction. How many clocks you have to run to get one instruction going. At the beginning of the decade, you had to run about 10 clock cycles to execute one instruction on the average. At the end of the decade, we went about 1 clock cycle per instruction. So every clock cycle, we get a new instruction graduated from that. And that gave amazing performance boost. And then the 90s, we had an era of diminishing returns. We kind of went from this 2-way superscalar to almost like 6-way, out of order, out of issue, branch prediction, everything is predicted, and this huge pipeline, amazingly complex machines. But we went from 1 clock per instruction to about half a clock per instruction. So we just doubled that kind of performance. And performance was below expectations, and projects got delayed and cancelled. One thing that saved, I'm not going to talk about that much, is at even this time you could get the clock frequency going higher and higher. And because of power and other physical limitations, we are also hitting a wall in clock frequency. So we are not getting, there was at that time, if you realize, everybody marketed saying how fast their machine ran. And they have stopped that because they can't get machines to double their frequencies anymore. So between those two, your performance kind of stuck. So that is why now we are starting in the new era of multicores. We need explicit parallelism. We can't build these large monolithic things that keep giving you performance every few years. That's stop. And we can build a sequential machine. What you get in 10 years' time will almost be the same as what we get today. But we get more and more silicon. It's doubling. The Moore's law still keep going. So what do you do with that silicon is kind of replicate and build more. I mean, that's where we are going into. And so if you look at what's happening, the unicores are all a dying breed. The last big one was Intel had these projects that tried to build very fast, amazing superscalar machines. All those projects have to get cancelled because they could not get the performance. The power was way too high. They could not get the power in there, and those things got cancelled. And as you see, there's more and more multicores are coming in there. So in fact, if you look at multicores are there here is in a big way. So if you look at all these machines, they are I only put the Pentium line of uniprocessors. And then from recent times, there had been 4 cores, 8 cores, and even machines that have more than 256 cores. Small cores, but we are basically going in there. That's a new trend. And if you look at the trend line, it's an interesting trend line going in there. So what I'm going to do now is switch gears because, let me see if I'm in the right slide. Yeah. switch gears because we have Mike Perron from IBM. We are very fortunate to have him here to give us a feel about the cell processor, because we are going to spend this month really getting to understand cell pros and really taking advantage of that. And he had done huge amount of work with cell. He's at IBM TJ Watson, and so he's going to next probably hour and a half, he's going to give us a lowdown on cell, and then I will conclude with a little bit more remarks about how we are going to do the class structure, and that will carry to the end of the day. Okay, Mike. Hopefully he had to catch a flight, so we will kind of go fast. Hopefully you guys, at least in the first lecture, go without too much of a break. So if things get too tired, let us know. So we'll see if we can put a break in the middle.